Good evening, ladies and gentlemen, and it's very nice to see that we have attracted so much attention. Hopefully, we will satisfy your curiosity tonight. I will go straight away on the presentation, and yes. So what you see here is a walkthrough during the earthquake of the 24th of August 2016 in Amatrice, which killed almost 300 people and left homeless more than 5,000. This is a walk down through the main street of Amatrice, and it's the best way to grasp the extent of destruction that this earthquake produced. As you can see, it's really a level 0 ground. As we walk down the main corso, we can see that some buildings are completely collapsed while others remain standing, even though they were seriously damaged. And in a strong event like this, as engineers, we would expect that most building designed appropriately would sustain damage but would stand up. In performance design engineering, we would call this a life safety performance target. Clearly, this didn't happen here, and we need to ask ourselves why. And so what we are hoping to do tonight is to go through some of the background reasons that have led to this situation, but also how we can, as structural engineers, produce results and produce alternatives to what we are seeing over and over. As we were coming on here, we just received an information that there has been an earthquake of magnitude 5.5 in north of India that was felt in Delhi, and hopefully, for the time being, no serious damage has been reported, but this was just half an hour ago. So the talk tonight will be articulated in two presentations by myself and by my colleague Tiziana Rossetto. I will go through the recent history of Italian earthquakes, and the whole presentation will be mainly focused on Italy because it's really our, let's say, experimental and field site continuously, unfortunately. As you will see, too many earthquakes too frequently occur there, with consequences that we wouldn't like to see in the future. Then we will, and some of the things that I will talk about are common to both of our presentations. We will then look at how to strengthen masonry buildings, and then Tiziana will show work that she has led and partly we have done together on to how to strengthen also reinforced concrete buildings and some joint conclusions. Without further ado, it's always nice to see a white. So this is the past, let's say, earthquakes in the past century, in the 20th century. And as you can see, the pictures are repeating themselves, and they show scenes that are very similar to the ones that I've shown in Amatrice. If we then look at what has happened in the more recently, many of you maybe remember the fall down of the serious damage of the church in Assisi Cathedral, of the vaults, damage in San Giuliano, which killed a school, only a school came down, but managed to kill 30 children, and then the earthquake in L'Aquila that killed 300 people, the one in Emilia, which was fortunately less deadly, and then this most recent in the central of Italy, with made much damage in Amatrice and a similar number of death toll. So we really need to, and this is continuing, as I said, but it's not new. In fact, if we go back ages, in the 13th century, we have already depictions in the same, exactly in the same places. This is from a church not far from Amatrice that clearly depicts an earthquake. You can see that the damage is in fact very similar, including the X-crack, to what you would see in a masonry building today. something has happened. Oops, let's try again. These are, again, pictures that comes from central Italy, and again, you can see a very similar problem. Nonetheless, more than 1,000 years have passed. We still live there, more or less in the same buildings. Very little has changed in terms of the fabric of the buildings, but a lot has happened in the last 50 years in terms, or even more, 60, let's say since the 1960s, in terms of retrofitting and repairing and strengthening masonry building. We could say with relatively little success so far. So we will see why some of this has worked and some have not, and what are success story and what are not. Before going more deep into that, I would like just to speak very briefly about the concept of and the process of recovery. So just after an earthquake, whether we are considering one single building or a number of buildings, we will have what we call an integrity loss. So the building is damaged, some parts are not working, structurally it doesn't work. In the first weeks following the earthquake, what we will look is at tagging, i.e. Classifying building depending on their damage status, debris clearance, and bringing things to storage if they are of any values. We will then consider shoring and putting the condition into a safe condition temporarily, so that we can then look at what happens next. And what happens next, notwithstanding the will to come back to the status quo ante the earthquake of the community and all the parties interested, usually takes months or years. Typically, first there will be a certain level of documentation plus analysis. We will try to understand why the building has been damaged, what needs doing. It's gone again? I don't know. Maybe there is a... If it stays on for too long, you just switch off. I will have to run. So let's say that in the next few months, we will go through the preliminary design and to try to understand all restoration in case of a valuable building. And then we go through the phase of approval. So during the phase of approval, of course, we require the technical approval, but we also need to find the money to do the restoration or the reconstruction and that it's clearly sometimes a large problem, depending on the wealth of the nation affected. It might be so large problems that other nations need to intervene to support it, such as the case of Nepal. In Italy, this is usually not the case. However, both L'Aquila and Amatrice earthquake have received European funding to help the reconstruction. And of course, these are also, let's say, an administrative system will have to be put into place in order to deal with all the aspects of reconstruction. Finally, once this is all sorted, we can go on site and start constructing and retrofitting so as to obtain and take back the building as it were. Now, in terms of what the technical content of this process is usually there isn't much leeway. There will be code of practice, especially in, let's say, Western countries, which are well established. In Europe and in Italy specifically, we revert to Eurocode 8. Part 3 has quite not so chunky, but improving sections. In fact, we are all involved in the review of that particular section on strengthening, retrofitting, and repair. And then there will be, of course, some further, let's say, codes and regulations which are specific to the state that we are considering. And what is worth noticing here is that sometimes as engineers we think, well, you know, the regulation is there, the regulation has been in place for a certain number of years, this is what is the state of the art. But in fact, it's worth considering that even the recognition of the seismic hazards in a particular part of the country might have only come about in terms of being regulated relatively recently. For instance, Amatrice was only turned into seismic zone 1 in the 80s, so relatively recently when you compare with buildings that have been there since the 15th century. And when this happened, of course, there were then source of funding for adapting and rehabilitating buildings which were not up to scratch with the new regulations. These are sometimes happen away from an earthquake. Then the earthquakes come, and we have the opportunity to see whether the retrofitting that has been installed has been, in fact, efficient and effective or not. And as a momentum of how effective this is, because what I've said for Amatrice also applies entirely to L'Aquila, it was only made into a seismic zone, in fact, even after the earthquake in even after the 80s, later than that, if I were remembering, to 1997 as a highest earthquake zone. And when the EFIT mission, of which I think Tiziana was the lead, went to L'Aquila, one of the conclusions was that this was a moderate earthquake that would likely have had many fewer casualties if the building were properly retrofitted or designed. So we start from that standpoint, and you can take that as our viewpoint for the rest of the conversation. Now let's go on to what we can do for masonry structures. So this is a typical building yard in L'Aquila 5 years after the earthquake. Yes, so this is one of the buildings, a masonry building that is being retrofitted. We can discuss whether this is the right type of retrofitting that should be done, especially the building being of historical value, but this is perhaps for another conversation. But I would like just to point out that when we are talking about buildings that are 500 years old or more, even if they are just a small residential to down to up house, they have important, significant heritage value, and they should fall under the UNESCO and World Heritage Site considerations. And one of the things that we are saying is that they are of value because they have authenticity, and the authenticity can be enshrined into the location and design, the settings, the material, the workmanship, but also the feeling and association. So that's why many of you, if you have been to the medieval small towns in the hills of Italy, you will find that you find them particularly charming. Yes, so you can lose many of these assets by way of retrofitting it too heavily, for instance, and hence that there a bit of a compromise needs to be had. And that compromise, however, is not just up in the air or in the will of the designer. There is sufficient guidance, both through conservation principles, but also through documents such as the ISO standards on the repair and retrofitting of historic buildings, which give that balance, or try to indicate what is the balance between keeping the conservation and the heritage value of the building, but ensuring life safety. And as engineers, we should always uphold the life safety as the first criteria for whatever we do to a building, because ultimately what we want is that people don't die in it. And yes, we can lose some of the authenticity, we can lose some of the materials, we can lose some of the value, but that maybe can be, and it's a permanent loss, but it's still a loss that is of lesser value than a life. Yes, so that should be at the back of our mind. So when designing, this is the point, yes, so when designing new measures, a remedial measure, we should try to, for these to act as sacrificial element, i.e. whatever strengthening we put in, it should help the building to act as a whole, but it should be the first to damage, so as not to damage the historical fabric. It should extend the life of the building, so start thinking about what it is that we are doing and for how long. Be retractable, i.e. some of the intervention that we might do today, they might be at the best of technology today, but they might become obsolete in 10 years, 15 years. Can we actually, makes a difference, can we actually dismount and alternatively substitute them with something more efficient down the line in 20, 30 years. Remember that this building have been there for 500 years, and we want them to be there for another 500. This is a very important thing from an engineering point of view, and very rarely actually put in practice. Can we observe the positive or negative effect while under construction? Yes, so we as engineers and as academics especially, and we will show you in a minute, we do a lot of experimental tests in the labs, but there is nothing like what is the actual performance on site. So can we actually measure that effectiveness? So going back at what we can do, these are the sort of strengthening strategies included in an earlier code promulgated in 1986. The approach there, from a structural point of view, the level of education of the average engineer at the time was the ability to design frame, whether concrete or steel frame, better if steel frame, and better if with what we call, I don't think the youngers of you don't even know what it is, admissible stresses, i.e. just a safety margin, and we consider that the behavior is elastic. Okay? So think of that, think of a frame, and then think of a masonry structures, and think how, as an engineer, would you alter the behavior of a masonry structures to make it behave as a stiff concrete frame. Yeah? So that was the, let's say, philosophy behind these provisions. And these provisions, by the way, were adopted in Italy and then exported worldwide, I would say. So, you would find some of the same intervention in New Zealand or in China and other places like that. So, it was really the common engineering knowledge at the time. So the idea was to include ring beams that you can see here and here. So these ring beams will be made of concrete. In the best of options, they would be anchored down the masonry, but as you can see the drawing here, there is no anchorage, so they will just sit on top of the masonry. Yeah. There would be then a rigid diaphragm, because as you have all learned in your seismic design studies, if the diaphragm is rigid, we can assume that the structures works like a 1 degree of freedom isolators, and our life is very easy. So yes, let's put in a rigid diaphragm. And the rigid diaphragm would, if it works well, and if the stiffness is evenly distributed, then prevent single parts from moving differently from the other. So also a good idea. In order to, so this is in terms of the global behavior. In terms of the strength of the single walls, then there would be mortar injection, concrete encasement with steel reinforcement, and formation of columns within the wall, again, then linked to the ring beam so as to form those frames. The use of steel ties was included in the norm, but if you have been, again, in medieval villages, you would have noticed that these ties were there since the 16th century, the 15th century, so it was already a solution at the time in order to keep the walls together. And indeed, what we see that works best in real cases are the be confused. Mortar injections, if the grout is properly designed to be compatible with the original mortar in the walls, and tie rods. So tie rods, even in a rubble wall, as you can see here, this is a case in a matrice, the tie has actually been successful in preventing the full collapse of the wall. So there is very substantial damage. It's clear that that house will need to be demolished, but the tie did its job of saving it from collapsing and hence allowing people to escape the building before it fall on their head. If the ties are better organized, of course, we can have a much better, and they are properly designed and linked to the internal walls and linked to the floors, then we can really have a box-like behavior. And as you can see, this is, for instance, a building in L'Aquila that had very little damage. And here you can recognize one of the medieval ties along with much modern ones. We have done some analysis at very large scale, so for instance, collecting data for hundreds of buildings in L'Aquila and looking at developing very simple capacity curves for them, and we can see that there is a clear marked improvement of the capacity besides what we see on site, but also we can then compute that improvement both in strength and in ductility when we look at the inclusion of anchors and the improvement of cohesion provided by injections. And this can also be measured by shift in fragility curves when we look at a site as a whole, and hence as the what would be the median level of acceleration that would cause damage to the buildings. To just provide a little bit more of feedback, let's see how we talked about ring beams and rigid diaphragm, and this was implemented indeed since from the 1970s into many churches and monumental buildings in Italy. These are three of the main churches in L'Aquila. They all had their roof retrofitted and their ring beam put in place there. This is the major cathedral, this is the Basilica di Collemaggio, and this is the Church of Santa Maria Paganica, and all these three the roof had been retrofitted, and for all three we see exactly the type of damage that we would have predicted without the retrofitting. So it's, and in fact, more, let's say, enhanced because of the retrofitting, because here, for instance, the beam pulled down the whole side of the transept, and similarly in Collemaggio. This is, it says monumental building, but this is not really a monumental building. It's an historic building, it's an historic house. It's extremely interesting because this house has been intervened at each story in each decades since the 1980 to today. And so we can recognize, let's say, the Italian guidelines in each part. So there has been some grouting, not very well done. There were a lot of pockets. There has been some attempts at stiffening the floors here by doing a very relatively modest concrete slab. Then more here there is a ring beam and a new concrete floor has been put here. This element here is the depth of the ring beam. So it's as you will see from this photo, from the same side, the depth of the ring beam is more than 600 mils. Yes? And this was done so that you can increase the height under the roof and basically create another habitable space, which you didn't have before doing the retrofitting. So, very good investment. But interestingly, because by the time they did this, it had become then fashionable to have timber roof, and it was said that no, timber roof is fine, as if they are properly designed and everything. You can see that actually the structure framing into that ring beam under the roof was made of timber, which of course could only but shear off because of the stiffness of the ring beam. Now, I just introduced a new set of guidelines which came about, were in preparation just before the earthquake in 2009 of L'Aquila, and they came into actual effect in 2011. So for the time, for the first time, it was explicitly mentioned that buildings need, that buildings need to be assessed for out-of-plane failure, and this needs to be prevented. So ring beams are still mentioned. It says that reinforced concrete ring beams are not so good, better to do them in reinforced masonry or steel, because that at least reduces the mass that you put in place and they have overall stiffness that are more compatible with the walls themselves. In this particular case here, you see a case in which the ring beam is made with brickwork and then is anchored back with FRP. This is one example of trying to define a different way of developing the so-called box effect. And then for in-plane strengthening and stiffness, grouting again is mentioned. The reinforced core grouting only in very extreme cases of very poor coherence of the wall lift, and shotcreting should also be avoided. And then the improvement of diaphragm actions, and again, for the improvement of diaphragm actions, what is referred to is the use, rather than using concrete slab, to use timber floors with different layer of planks, possibly oriented in different direction and nailed together, so as to create that sort of stiffening effect without increasing the weight and the mass of the floor. So just as an element of example, this is what is recommended for the wall, to try and use FRP to hold the walls together. There have been a lot of study on this particular type of strengthening. It does work in some cases, it doesn't work in other. There are also important issue of how this work in the long term with environmental conditions, humidity, and so on. As I said earlier, shotcreting should not be used, but we saw plenty of that in L'Aquila as we were going around during our recovery missions, some 3 or 4 years after the earthquake. I also mentioned that reinforced grouting should not be done, but here you have plenty of them. You can see this wall, there is one every half a meter, and these are made with FRP strands, which are then opened up to provide some anchorage. But basically, you are drilling an hole in the masonry at a distance of less than 300 or 400 millimeters, yes, for the whole wall. Some good things were also going on, such as putting proper anchorage across the wall. This is a palazzo that was done trying to use the same strengthening system, such as ties already used in medieval period, but improving them. And the results, as you can see, they are not obtrusive. They really don't disturb the architectural value of the building. They are regularly spaced, so they are not put up haphazardly, but they indeed improve the situation. One of the problems that we have with all these type of interventions is that they are all aimed at increasing strength rather than increasing ductility, or the anchors do improve the ductility a little bit, but certainly they don't improve the level of dissipation unless the walls start rocking and the anchors start yielding. So one of the active lines of research that we are pursuing at UCL is to look at dissipating devices that we can put in series with traditional or stainless steel anchors and based on friction. So here you can see how they would be fit at a T-junction between walls. This is the dissipative device, and these are some of the tests, just pull-out tests that we have performed to determine the level of ductility that we can gain. So these are anchors that have failed in without the device, and anchors that instead we can make work as the device. So the device is a very simple object, so it's just a conceptual idea. 2 plates and an element sliding within, and the friction is generated between the plates by just torquing bolts to controllable degree, so that we can actually design it. We know how much torque we are giving, and we know how much pressure we are posing. So these are typical output tests. So one of the things that we are investigating is how the friction coefficient changes with the number of cycles and with the frequency of cycles. So, and this is very important for the long-term use, and for the fact that, of course, in an earthquake condition, cycles will not be stable as we see here, because there will be different level of input accelerations and different level of equivalent force at the response, but also different level of displacement expected. And we can see that the element remain, so for relatively modest vertical loads, or let's say forces that activate the displacement, the cycles are very regular. If we increase or double or triplicate that value, then the element of dissipation, so the traveling of the two flats are subjected to some disturbances. And indeed, we can see here that after 50 cycles, there has been quite a little bit of wear and tear. So aware of this, what we have been doing very recently, and this is just hot out of the computer. So we are looking at how that performs in an abacus models. We can clearly see that the pressure in this particular layout is confined to mainly these areas, and indeed this is the areas where we get the wear and tear that we have seen in reality. So then, let's say the next generation of this same concept is actually to have a more rounded inner part, possibly also lighten it with, because this is stainless steel, so we're looking at other alloys that can give lesser mass, and we can already see that the distribution of pressure is much more even. Clearly there are no sharp edges, and hence also the way in which the wear and tear develops is much lower. We have put one of these devices into a church in L'Aquila just after the earthquake, and we left it there for a year and a half, and we were able to actually pick up some of the tremors, some of the micro tremors that came up afterwards, and look at how it reacted for these micro tremors. Of course, was not activated because the forces were too small, but we were in a position to at least see what was going on. And then we further analyzed this with more numerical analysis to look at the behavior within real structures. I think this concludes my parts. So just as a matter of initial conclusion, the major issue when retrofitting masonry structure is the inherent lack of ductility of the original material. Improving connections among walls with ties and improving cohesion through grouting of rubble walls, of repointing, substantially improves the response for moderate earthquakes, ensuring light safety by controlling overturning and collapse. Conventional strengthening is still substantially based on improving strength rather than ductility, on energy dissipation, and has proven not to be very effective, as we have seen. Dissipative device based on friction can be designed and manufactured to be no bigger than a brick and inserted directly into the masonry fabric, and they have the advantages over other type of dissipative device that they don't need much maintenance, they also have very stable cycles and dissipate a substantial amount of energy for relatively little movement. I'm now, and I think, I'm sorry if I've taken a little longer than I was expected to. Tiziana, please.
Thank you, Dina. So what I'm going to be talking about is, let's say, the more modern construction. In Italy and in many parts of Europe, there was a large boom in the construction of reinforced concrete structures after the Second World War in response to housing needs. And not surprisingly, in the last 20 years or so, these have actually shown a disproportionate amount of collapse in earthquakes. And due to their high occupancy, they have also caused quite a large number of casualties in recent earthquakes. Being built after the war, typically in the 60s, the 70s, and with the first Italian code, for example, coming out in the 1975, the vast majority of these structures are not designed to any seismic code, and therefore tend to fail in quite a brittle manner. And some typical types of failure that we see in earthquakes are shown by these images. Sorry, I'm not sure. Yeah. So soft story collapse, or in any case, damage concentrated in the top and the bottom of columns, which is very dangerous because then the structure loses its capacity to carry any vertical load or its own self-weight, and therefore it can be very deadly. And in other cases, again, failure at the beam-column connection, which has the same effect. Essentially, it's like having a plastic hinge at the top of a column. So again, causes the devastating or drastic failure of these structures. So having said these, any strengthening procedure has to take these two sorts of failures into account. It needs to think about failure of beam column connections, and in particular needs to try and reverse the weak column strong beam mechanism that is quite predominant in these older structures. And there is a pressing need because they're high occupancy and potentially very deadly. So unlike unlike masonry buildings, there are not so many constraints in terms of what you can do or what you can't do in a reinforced concrete structure. In fact, one of the most common retrofitting technique is the addition of structural elements. So, one of these approaches is, for example, to add a shear wall or an additional wall to strengthen a particularly weak or low stiffness floor. However, such a method is actually quite disruptive to common activity, is expensive, changes completely the global response of the structure, and often requires also intervention at the foundation level in order to carry the additional shears, etc. I'm just going to mention base isolation and supplemental energy dissipation devices. These are used for reinforced concrete structures. Base isolation in particular has become quite popular in some of the retrofitted or new buildings in Italy post the Aquila earthquake. However, they're actually typically very expensive, and the expense is such that it's actually prohibitive for most residential type constructions, so it would be used mainly for critical infrastructure or critical buildings. The next most common retrofit technique are reinforced concrete jacketing or steel jacketing of structural elements. These interventions are at the element level. They are less disruptive than things like shear walls, etc., but still require quite a lot of intervention, do carry out some disruption, and, for example, in the particular case of steel jacketing, have the issue of corrosion associated with them in the future. FRP wrapping has been gaining significant traction in Italy after the Aquila earthquake. I'll show you some examples shortly. And these are just some pictures showing how the fiber reinforced polymer is commonly used to increase the bending, the shear capacity, and the ductility. So, for example, by confining the concrete in a column, they provide the additional strength and additional ductility of those elements, and equally also in beams. Note here the particular thing I want to show is this is not actually from a practical application that I've seen. It's from a guidance of good practice picture, and shows essentially that the wrapping for the beams is passed through the slab and anchored across the top. So it wraps the entire beam. In practice, that commonly isn't done. So this is a picture from L'Aquila. What we see here is a wrapping of the columns. I want to just highlight that actually you have a relatively small beam, relatively small column, okay, an extremely large slab. Generally, slabs are not considered within the design of retrofit solutions, and this is an issue I'll be talking about. They are there. Why are we ignoring them? This is another picture taken again from L'Aquila, where you can see that there's been quite substantial retrofit through FRP wrapping of columns. And this is a gentleman showing us the FRP wrap itself. But what you can see quite clearly here is that the wrap around the beams is just sort of laid around the surface and not anchored in any way or form. So whether it's effective, I don't know. Again, a global retrofit of, in this case, a school in L'Aquila. They have decided to wrap the external beam column connections, and quite interestingly, for those who are seismic engineers here, actually created an additional problem by strengthening this. They've created short columns that are likely to shear off in the case of a future earthquake. So there is the guidance, there's the good practice, and then there's what happens in the field. And And partly one of the issues of what happens in the field is because the guidance doesn't take into account practical considerations in terms of applying the actual FRP strengthening. So let's take a step back. Why is FRP interesting? Well, in essence, it's quite a strong material in the direction of the fibers. It shows basically elastic behavior and can sustain quite a large axial load and is quite easy to apply. It has a high strength to weight ratio, so it doesn't apply additional mass to the structure. It doesn't corrode compared to, say, steel. And there's little impact on dimensions, and it can be aesthetically pleasing. You can, paint it and make it look nice, etc. It does have significant drawbacks, and some of those are the low ductility and the risk of rupture, but if appropriately designed, that doesn't seem to be a problem. The bond to the concrete is actually critical, so the concrete surface has to be prepared, angles have to be smoothed, and some care has to be taken to make sure that bond actually happens, and indeed additional anchorage is often necessary through mechanical devices. There are durability issues in the case that it's exposed to UV light, etc., but again, appropriate care or protective covers can be put on, and poor fire resistance, which again is a concern, but again, you can have interminescent covers or different types of interventions, etc. So I'd like to give you an overview of a research project that I worked on with Dina and with colleagues in Porto University in Portugal on essentially the FRP retrofit of interior beam column connections. Why interior? Well, if we look at the literature, the vast majority of the literature of experimental data out there is for exterior joints. Very few regard interior joints. Very few include the slab, and what we've said before is the slab is there, and it's one of the, if we want to design a practical intervention, a practical strengthening solution, we have to take into account what is there and what the contractor will have to deal with. So again, that's an element that's missing from the literature. And another thing that is quite scary is that a lot of the specimens tested are at a reduced scale. What that does is it shows a much higher retrofit efficiency. If you wrap a column which is at a reduced scale, the dimensions of the wrap, the efficiency of the wrap on that column is much greater than if it's at a larger scale, because you're not scaling down the wrap material itself. It's quite difficult to do. Without the slab, we also see that there's a higher efficiency from the literature, and that's quite scary. I mean, it seems to be over a 20% difference in terms of strength if you include the slab or not in terms of efficiency. So we saw from the literature that there was a need to actually develop realistic retrofit solutions for realistic geometries, and that testing was needed at full scale. And so we embarked upon this challenge. That's why it was called Challenging Risk as a project. And we decided on a case study structure, which was a reinforced concrete moment-resisting frame designed to the 1967 Portuguese standard. This is a typical standard. We could have chosen any from Italy or from Greece, etc. It sort of represents Mediterranean-type structures with the typical deficiency seen there. So low flexural capacity of the column versus the beam, quite clearly in the size of the elements and the fact that you have a big there. Inadequate spacing of shear reinforcement and transverse reinforcement, so not providing maybe the shear resistance we would expect nowadays, and also no joint transverse reinforcement. So these are some of the inadequacies that are very common in reinforced concrete design of the era. And we were looking at, say, the beam column connection within the second story of a sort of a 4-story type house. So this is a sort of typical residential construction. Before we embarked upon the full-scale experiments, of course these things are expensive, we decided to build a abacus model of the experimental. We only modeled half the structure, and because of symmetry, and essentially we're trying to understand, first of all, the effect of the slab and the transverse beams. Note, these are often ignored in experiments in the literature. The result of that is they're also ignored in codes of practice. So the increased efficiency that we see of the retrofit is reflected in the codes of practice and in the guidelines, which ignore slabs and transverse beams. and this is slightly worrying. So we wanted to understand the effects of slabs and transverse beam on the response of the beam column connection and on how we might identify different retrofit strategies. So this is just a little bit more of an example, and we carried out a quasi-static analysis, just pushing essentially the top column, allowing the beams and the slab to slide, restraining them at supports, at sort of points of contraflexure. And what you see is if you have the transverse beams and the slab, this is the sort of area of failure. It's very much concentrated in the top column. It's what we see in the field, so it's sort of expected, yes? It's the sort of this column failure with some level of damage within the joint. What we see is quite a high strength and relatively low, well, reasonable ductility, but not very high. If instead we go to ignore the slab, but we have the transverse beams, we see that the failure mechanism changes quite significantly. There is damage within the joint, there is damage in the beams. The beams are activated, whereas here, oh, I don't know what happened there. Okay, whereas in the first scenario, the beams are not activated, there's no damage, no deformation in the beams pretty much. So here it's looking a little bit more favorable in terms of putting the damage within the beams than in the columns, and you have almost no column damage. If we remove the secondary beam, you actually get concentrated damage solely in the joint. Okay, so most experiments out there, most guidance is based on experiments that have this sort of configuration. So retrofits are looking to basically target that sort of damage, so damage in the joints, whereas in reality the damage is happening in the columns. So we're dealing with two completely different strengthening targets here, if we assume what's in the codes and don't take into account what's there in practice. Okay, so this is sort of the premise. So essentially what I want you to take from that is the fact that if we're ignoring slab and transverse beam, we are actually targeting the wrong strengthening. We're targeting the wrong part of the structure to strengthen. So we use that information to design full-scale experiments. We carried out experiments on 4 controlled joints, 3 repaired joints, 3 retrofitted joints, and 3 columns. I'm not going to present all of that information, but I want to show you some of the videos and some of the results of our experimental campaign. What you might see is interesting is in this case we actually tested the joints horizontally. This is one of the quirks of the facilities at Aveiro University where we did the testing. So essentially this is the bottom slab, this is the bottom column, the top column is at the top there, and it's resting on its side. And this is part of the frame that is restraining the upwards, downwards movement or equivalent of the beams and the slabs, but we are allowing them to move in a horizontal direction freely. There are jacks at the top applying, and at the bottom applying axial load, and then we are pushing the top column sideways and displacing it under different cycles. This is another rendition of that. What I want to highlight is the fact that we actually implemented a higher axial load in the bottom column than in the top column, again trying to reproduce realism, the fact that the column below the joint will be subjected to a higher axial load. We subjected the structure the sub-assemblage to a series of cycles. This is quite common, so starting from small cycles and going bigger. And these are just some. It should start, I hope. No? Click again. Aha, voila. And this is just a mashup, essentially, of videos from the actual test. So this is an image taken from above. And what you can see is the strengthened columns. In this case, you will see what we call strengthening scheme A, working in conjunction, the actuator pushing there, and the beams able to move quite freely in the horizontal direction. Okay. Also the fact that we had a hell of a lot of monitoring equipment on there and lots of people helping us to actually do the experiments. So with the tests, what we did is we set up 3 main control specimens. The first one was, as we discussed before, having a control specimen that had the beam column connection with slab and with transverse beams. the same exact geometry, but designed now to Eurocode 8, so to modern standards. And also we took a control specimen without either slabs or transverse beams to see what the retrofit effectiveness would be of this arrangement compared to sort of the cross, or the typical cross. So with the first control specimen, the one C1, which is the non-seismically designed structure with slab and transverse reinforcement, we see that actually our prediction from the numerical model realized itself in the lab. We got concentrated damage in the column ends at the top there, very little damage at all in any of the beams. Actually, that shows the sort of the slight cracking really of the beams in that location. And so, you know, actually we were quite confident our numerical model actually worked at this point, but also we're able to target and to think about how we might design the strengthening. If we looked at the same geometry and reinforcement dating without slab and transverse beam, so this is the cross geometry, what we saw was the different failure mechanism, the failure concentrated at the beam column connection, exactly like we had seen in the numerical model. We see a completely different failure mechanism, which is really the point. Of course, a lower strength, relatively high ductility in the cross, which is quite interesting, and higher strength degradation because of the failure in the joint. So I'll be showing a series of these with C1 always in there as the control specimen, which is our non-seismically designed element. But essentially, the key element is these different targets for retrofit. If we look instead at the control specimen designed for Eurocode 8, as we would expect, you can achieve a much higher strength, actually 96% higher strength than for the non-seismically designed structure, a much larger ductility, again also you know, your displacement at failure is much, much larger. But also looking at this, we got quite scared and we said, oh my goodness, how are we going to achieve that sort of behavior, the Eurocode 8 behavior within a retrofit? You know, how do you achieve a almost 100% strength increase and, you know, how do we double the ductility? So we looked into Eurocode 8, and within there in part 3, there's some sort of, I'm not sure if it's guidance, etc., but, you know, it says it's appropriate to target about 80% of the strength of a Eurocode 8 specimen with similar ductility. So that's what we put ourselves as a target for the strengthening. With that in mind, we decided to come up not with just one strengthening scheme, but to look progressively and systematically at 3 different strengthening schemes with very different objectives, taking one step at a time, essentially. So in scheme A, because the damage had basically happened within the top column, what we wanted to try and do is increase the strength and increase the ductility, mainly the ductility of the structure by connecting the top column and the bottom column. So because all of the damage was concentrated in the top column, we wanted to activate also the bottom column. In scheme A SW, which SW means selective weakening, we used a quite novel idea, which we was inspired by a paper by Stefano Pampanin, which basically threw out there the idea, and they did a first preliminary experiment to say that actually, if you wanted to change the failure mechanism from a column dominated to a beam dominated, then the only way you could do this was to actually weaken the slab. So we introduced cuts within the slab, therefore weakening, you know, stopping it, the beam acting together with the slab as a composite, and again applied a retrofit scheme there. The idea here was to actually activate the beams and to see whether that would happen, not necessarily to increase the strength, that's part of the first one, but to actually activate the beams. The third scheme, scheme B with SW, was actually trying to achieve all the objectives of reaching that near behavior to Eurocode 8 specimen. So increasing flexural capacity of the beam, ensuring flexural strength of the column is higher than the beam, so reversing the failure mechanism, as well as strengthening the joints. So we wanted to change the failure mechanism and strengthen hearts. So these are the 3 schemes, and we'll be comparing them. So the first scheme looks at strengthening essentially the columns, top and bottom, but not only that, we also wanted to link them, and we linked them through a well, we'll show you the procedure step by step. We link them through passing a strand connecting the top columns to the bottom columns. So the procedure here is you have to drill some holes into the slab. The slab is there at the corners. And we then applied one layer vertical FRP to the top and the bottom columns. We developed these strands, which were just basically rolling the FRP material into essentially to form like a rope. And we passed them through the holes that we drilled. And within them, because the first time we did it, the strands ruptured really early, and we realized you can't have any sharp edges around FRP, we encased them within a plastic tubing system. So holes, plastic tube, stick the FRP strands through, splay them, and so that they provide some level of anchorage. On top of that, we added mechanical anchorage to help those strands act together. And then we applied some confinement fibre reinforcement wraps around the column ends, again to improve the ductility of those elements. So, and finally, to help with anchorage and also help distribute the plasticity, we also put some more fibre reinforced polymer wraps, but of smaller, lower number of layers above. So that was it. What we found was actually we did get the behavior we wanted. It did connect the top and the bottom slab. So we changed the top and the bottom columns. So we changed the behavior from this to this. We did achieve a higher strength, a higher ductility with this arrangement. And this is, let's say, the least invasive of the strengthening procedures that we put forward. However, we still got failure in the column. So we were not failing the structure in the beams, not activating the beams at all. So it was still a column failure, although it happened at a more retarded state, and we had distributed damage at the top and at the bottom of the column. So we connected the two in that way. So okay, we achieved what we wanted to do, but we didn't reverse the failure mechanism. So within the scheme with selective weakening, our objective was to weaken the top slab to ensure increased rotation of the beams. So let's get the beams participating now. We know that we can get the two columns working together. Let's also get the beams participating. And so we maintain the same strengthening essentially, but cut slices into the slab. So deconnecting it from the beams in this way. Quite labour intensive to do. Our researchers weren't that happy. But what we saw here was that actually we got failure in the beam joint. We got higher ductility. We didn't get a higher strength. So this is the green is with the slab weakening. So we got roughly the same strength as the control specimen with no strengthening. But we got a larger ductility. We did activate the beams. So we did get damage in the beams, but we still had failure around the beam column connection, which is not great because that again translates into possibly a bad failure mechanism. You've got hinging at the top and the bottom of columns. So we decided to do more. And at this point, we had connected the top and the bottom. We have activated the beams through the selective weakening. But in order to move the plastic hinge away from the joint, we strengthened the joint in shear, and we also strengthened the beam. So now we extended the cutting and created a new failure plane, or a new sort of weaker section away from the joint. So we definitely constraining the damage within the beam, which is a good thing. So that was the idea. And the idea was to try and achieve the 80% performance of Eurocode 8. How do we do the retrofit? I don't know whether this will work. So this is what it looked like. We started with a cut through the slab, the vertical layer of reinforcement, as we did before. Again, connecting top and bottom things, so exactly the same procedure we were talking about before. Then we put strips at the bottom of the transverse beams, strips across. We had to drill holes through the other beam to get them through. And because the slab was already cut, it was actually quite easy to confine the beam itself, because we already had cuts through which we could pass these parts. Okay, stuck? Aha. This is, oh, sorry. Okay, I've gone forward. But what I'm showing here is essentially a picture of the top column. It's quite difficult to get the whole joint in a picture. Typical of the top column and its behavior of the control specimen compared to when you have the strengthened with slab weakening, etc. And what you can see here is obviously this concentrated failure at the end of the column, which is avoided here because we've activated quite a significant amount of damage now in the beams, but further away from the joint, so there is no damage around the joint. These are actually moving at different rates because this one underwent much larger displacements than the other. So, what did we achieve? Well, the latest strengthening approach did achieve a much higher strength than just combining the two columns. It achieved the same level of ductility as we saw by cutting into the slab. Of course, it's a combination of the two, and it's almost a perfect combination of the two, strangely enough. So it showed the highest no joint damage, failure was in the beam, highest ductility, 6.8, which is quite large, but also very good softening behavior, and although we didn't achieve the full strength of Eurocode 8, it was quite close. So you can see here there is actually damage within the beam, but it's mainly concentrated away from there. So that's your comparison. That's 80% of Eurocode 8, which is the blue, and what we achieved was the red. So not too bad. That's the same thing, sorry. If we look instead at what happens when you have the effect of the slab, and if you remove the slab and the transverse beam, and you apply the strengthening, so remember having that cross, and you apply the strengthening, what we find is the blue bit here. So you get a much lower ductility than if you consider even the cut slab and the strengthening procedure that we have put in. You get the highest retrofit effectiveness, and this is the scary bit. You get a 51% retrofit effectiveness if you're strengthening that. And you avoid joint failure, of course, because you're wrapping the joint, essentially. So that's quite scary. What we do find as an advantage of weakening the slab is that actually, because we're then intervening on only the beam and only the columns, we can use current code guidance. And if we use the current code guidance, we find that there's actually a very strong agreement between the experimental moment capacity and the predicted moment capacity from the code, that are given by the strengthening application in the codes compared to what we see in the laboratory. So if we're looking just at the columns or at the beams, retrofit beams, we find very close matching with the current guidance. So if you weaken the slab, because the codes assume no slab, then actually you can use the codes. So it seems a bit odd, but that's what we found. So to conclude my section, essentially, we found it extremely important to look at realistic specimens and realistic geometries to take into consideration practical applications in our design. There are still quite a lot of challenges out there in designing retrofit and in considering real application. We found that our scheme B, which uses the selective weakening and strengthens also the beams to avoid failure in the joints, provides the highest ductility and strength, the highest energy dissipation, and the best post-peak behavior. And we do worry, in a way, about this higher retrofit effectiveness for specimens without slab, and the fact that they have been used in the past to, to calibrate codes, guidance. But if you weaken the slab, you can actually use the guidance that are in existence to design the FRP. So that's the positive thing of it. Perception-wise, weakening stuff is a bit more tricky. But anyway, I'd like to invite Dina for the final... Oh, me? Okay. We have some final remarks, which are joint between myself and Dina. And I think overall, in our experience over the last years of research, and I won't say how many because I will show our age, we've seen that the earthquake engineering community has grown in its sensitivity towards the importance of preservation, promoting research in this area, and into new strengthening and assessment methods. Code provisions have evolved with a lot of improved knowledge in there in terms of hazard, as well as in terms of knowledge on the strengthening processes themselves. We still need to ensure that engineers obtain the appropriate training. Strengthening is not a traditional discipline within most civil engineering courses. And what we find consistently is the quality of the actual applications, interventions in the field, in practice, make an enormous difference to the delivery of the let's say, improved performance that we would like to achieve. So what we find is also that the economics of developing and installing dissipative devices can be overcome, as shown by prototype devices which are manufactured in small sizes, relatively cheap costs. So these are becoming more and more affordable and more feasible to use in practice. So with that, I just wanted to highlight some of our sponsors for this research, and actually also acknowledge the large number of researchers that have contributed to this body of work. And this goes back many years, and I'm sorry that we haven't mentioned them all. They are actually quite a large number. Some of them are sitting around in this room, so I invite you to talk to them a bit later. But thank you very much.